Hello everyone, I'm Yoo-Jin Yang from the Korea Astronomy and Space Science Institute. I'm working as a project scientist for Korean SPHEREx science team. And today I will take you to the journey to study the technology and science behind the SPHEREx space telescope. And let's learn more about what this space telescope means for our future. SPHEREx is, in short, NASA space telescope, and this is a NASA-led mission, and Korea and Kashi is participating from the beginning, and we are contributing science and instrument and technologies to the NASA-led mission. So in quick summary, SPHEREx observed the universe in 102 infrared colors. Okay? And we are not just observing on particular stars or galaxies, we are observing entire sky, all sky, okay? So by doing that, using this kind of data, which is astronomers call spectra, which is 102 intensity as a function of wavelength, this is a spectrum. Using this kind of data, we can measure the distance to the galaxies, stars, and for example, and then we can make a 3D map of the universe. That's our goal. So this is how the SPHEREx looks like. SPHEREx is a rather small telescope compared to JWST and Hubble. So it's only 20 centimeter wide aperture telescope, but it can actually see a large part of sky at once. So if you point at certain part of sky, you can see the 3.5 degrees times 11 times 3 degree at once. So it's very huge compared to the other telescope. This is probably actual size, actually. Yeah. So this is actual size, probably 2.6 meter, right? Yeah.
I was wondering actually.
Yeah. That's it. Yeah. As I said before, SPHEREx observing infrared, okay, between 0.75 micron to up to 5 micron. That's infrared. Because SPHEREx observing the infrared, it has to actually cool down, because not only the sun, Earth, and the moon, the telescope itself radiates a lot of infrared energy, which you cannot see. Also, I can radiate a lot of infrared light. To prevent that kind of light interfere with our observation, entire telescope should cool down to almost minus 200 Celsius. For that, SPHEREx take a very interesting technology, something called V group at the small thermal plate at the bottom. And it employs something called potential, this kind of conical shape, which has 3 layers. And light is cooled down by the red path of the photon, so it can radiate through the space through its energy. So this is cooled down up to this telescope. This part is a core part of the telescope. It's something called payload system, and this bottom is spacecraft. So this is driving your telescope in the orbit. So it's engine, your bus, okay? But this green part is your payload system, actual telescope. So in Korea and Kashi make a test chamber and put this part of the telescope into our big fridge, big chamber, and test it. So that's our contribution. Very unique part of the SPHEREx is something called linear variable filter. This telescope has 6 of them. So when you take a picture, it produces 6 images of this each filter. So we call it LVF. So I think that this is very uncommon. It's a concept that even astronomers didn't know much about. So this LVF filter is a filter that transmits certain specific wavelengths depending on the position. So in this right panel, you can see that a red dot, that point only transmits this 1.1 LED light. And if you far go to this left side, the blue part, it only transmits this blue light. So central passband actually can transmit, it varies across the filter. So linear variable filter. So this technology is very new, as I said before. And then Kashi is the first team that bring this into space. So this is something called NIS satellite. So a few years ago, Kashi developed this kind of technology and put on the space and observe some part of sky. But this is a very small mission. And from this experience and technology, we're able to participate in prestigious NASA space missions. So let me briefly explain that what is this linear variable filter and this technology. So when astronomers taking picture of observe the universe, galaxies or stars, how usually done is that like this. when you have red filters on your telescope and take a picture, so your black white picture, and then put the green filter and take a picture, and blue filter take a picture. So you have RGB channel, but there are only 3 colors, right? So 3 colors enough usually, but the more colors is much better, right? So if you have many colors, you can carry more information, because more colors means that you can split your light more finely, then you can get more information about the stars or galaxies. So right now, for example, 17 filters, right? And then I said how many colors we are taking picture?
102.
102, exactly, you pay attention, right? So 102 colors. So you need to bring 100 glass of the filters to the space to get these 102 images and spectrum, right? Obviously, that's not possible, right? So that's why astronomers and engineers develop these special filters. Idea is very simple. You cut a piece of this filter and put the bottom, cut each one and stitch together. So you got just one filter with rainbow colors. The filter looks like this. Central wavelength of filter is continuously varying, not discrete. Of course, type is not simple. Even though you want this kind of filter, reality is says something curvature. You don't know that because even if you make this filter in the ground, when you fly it, you don't know actually how this curvature is present. That's why our COSI chamber and NASA together put this filter and telescope in the big chamber, and we measure it, this curvature and how this color is distributed on the filters. That's our major expertise and contribution. So the LV filter is brand new, so we are not able to observe the sky before. I could take a picture like that. So because we have LV filter like this, and we are now observing new technique, which is we can stepping through one by one, little bit here from here, bit by bit. Oh yeah, you can see that we can stepping through this universe, this galaxy, right, one by one, and every point of this galaxy should go through all these rainbow colors. In the central part of the galaxy, it exposed every colors, right? Now you can create these colorful images, hence spectrum, right? This is a way to observe the galaxy. Yellow half circle is where you can point without directly looking at the sun or moon or earth, because you cannot see the sun directly. So moving around in this limited range, you can stepping through the sky. Usually you take 4 exposures, 1, 2, 3, 4 sometimes, or 5 times. So, and then we are reaching the edge, and then now moving toward the bottom. So this is just one example, some part of sky. And this is how done in the all the way into space in the lifetime of the SPHEREx. And you can see the right panel that how the coverage filled up. Like a painting, you are rolling the paint on the sky, but you have to go through all the corner of the universe to get the information. So after 6 months, because Earth is rotating around the sun, we naturally cover the entire sky in every 6 months. In SPHEREx, repeat this process 4 times for 2.5 years. Hence, we can achieve the all sky survey in our entire universe every 6 months and 4 times, basically. So that's our goal.
Okay, so now I think I get it. But doctor, what color exactly is space? I mean, is it as colorful as we see in movies or videos and pictures?
That's a little complicated. When astronomers are taking pictures, all the images are black and white, only that reflect the intensity at that wavelength. If you take a LED filters, it gives you how much this galaxy emits light in red color. Okay. So it's like usually black and white. And then when you see the beautiful image of the space, like back in this background, what we astronomers do is that take RGB image, red, green, and blue colors, and make composite to give you the low, kind of close, naked eye view of the images. But in the SPHEREx case, we are observing what wavelengths?
Infrared.
Infrared, right?
Now I can pronounce
And you can see that infrared or not? No, you cannot see it. So you have to visualize. You have to show something. We have images, and there's some intensive map of some galaxies on space, but I cannot show you, right? So for that, so we are taking pictures in different wavelength infrared colors and put some colors to give you a good impression about this one. And also it helps us to understand the physics behind this system. Okay, so size matters. Probably you may wonder that why we are building and sending up the new space telescope into space, putting a lot of money. Right, so you know that you are familiar with something called JWST and Hubble Space Telescope and SPHEREx. This is relative size, okay? This James Webb Telescope size of tennis court. Entire thing is tennis court. And then Hubble Space Telescope is like a US school bus size. A big bus, huge bus, filling this entire room. And SPHEREx is about this big, okay? So you may wonder why we are making this variety of the suite of telescope is something like this. So this is probably you have seen many times if you are interested in science and spaces, because this is one of the first image of the James Webb Telescope, which is about $10 billion mission, very expensive mission. And this image blows us basically everyone, every astronomers and all the public's mind, because there are so many details and so many galaxies in the background, tiny bit of the data, all the galaxies billion light years away. And you can see that all tiny details, structures and the filament on some kind of arc and the bright stars, something like that. But this is a very powerful image. However, if you compare that area of the image with the moon, it only occupies that amount of tiny bit. So if you see that, if you just imagine the moon, and that the tiny bit of the dark area is actually that part. So this JWST image is actually going through a really small, tiny area of the sky in very detail, right? So, and that one, the 3 panel is that how much SPHEREx can see at once. In single exposure, SPHEREx see that these all green square is a huge area, about 3.5 degrees. If you compare that with the size of the moon, only moon is filling that small part of the sky.
Oh, but doctor, I'm just curious. So the James Webb or the Hubble, it's capturing so small compared to the new SPHEREx, right? So the SPHEREx is much quicker and wider. Like, how's it able to do that?
Yeah. So that's the kind of decision. What is limited for this kind of astronomy and space mission you usually live life? What is the usually limiting factor in your life?
Money, time.
Money, exactly. Time, time or money, right? So you have a limited amount of money. So in the James W case, you have $10 billion, and SPHEREx case about $0.3 billion. Okay, so you have limited amount of money, and how do you spend? How to make a biggest return out of it is a science question. So astronomers can make a decision early days when you're developing this kind of telescope. So James Webb, okay, we have to go through the end of universe, right? So make it bigger, but if you make it bigger, you cannot see all of them, right?
But then the image quality is different then?
Of course, yeah.
Oh, it's different.
So that is a spectacular image quality, but the SPHEREx cannot see that much detail.
Okay.
The James Webb telescopes go really deep, but only tiny bit of the skies. But SPHEREx go to a little bit shallow because small telescope can go really much further and less detail, but it can go entire skies. So the SPHEREx is actually can see that 150 moon at the same time. Even more than that, SPHEREx is rotating all the way, all the time, right? So from this one, you can scan entire sky. So that's why SPHEREx is designed for the survey. You can go to wider area and find interesting object, and then follow up with JWST. That's the astronomer's tactic. And the first slide. So we finally launched the space telescope and opened the shutter and take pictures, and we got the first images. So let me go through this image one by one a little bit. So I was emphasize that this is the first slide. So you usually say that, okay, this is first slide, first image taken by certain telescope or certain instrument. Usually that's maybe take many pictures. Oh, this is not good. This is not good. And throw away and present to you, oh, this is our first image. It's not like that. SPHEREx, this is the first image, okay? We opened the shutter and got this perfect image. So this was so successful mission. everything is focused, and all the sensitivities, all the status images are as we expected. I show you 3 squares before. So this is 3 squares, 3.9 degree and 11 degree wide area. And then I told you that before 6 LBF filters, right? There are 3 of them, and the other part is 3 other part of the skies. So, but we are actually looking at exact same region. So you can see that, for example, these 3 stars, right?
Yeah.
There are 3 stars is exactly matching.
Yeah.
We are seeing the same part of sky, upper row and down row panel is basically we are watching same sky, but through different LBF filters. You may expect colorful images, but this is black-white. Yeah. So you put the LBF filter and take images, and you got the intensity, how bright it is, each position of each part of the sky. So this is the black-white image. But let me paint for you. I mapped this color, painted this image as a function of the wavelength. So each color means that I'm observing, we are looking at the sky through that wavelength. So if you zoom in a little bit, bright part, this huge dot is a bright star. If you see that it's a green square area, zoom in, and you can see the start now, you start seeing the details of the universe. You can see that this elongated shape is very nearby galaxies. And if you zoom in further of these blue squares, you can now see the dots, right? Oh. And these are very faint distant galaxies, and we want to measure distances to this galaxy and create a map. I mean, you can imagine that how different with these JWST images. They are different, right? There's no much pretty arc or pretty details, but there are many more galaxies in this picture. So this is technique that we are trying to do. So we are not observing actually entire exoplanet system. We are just look at random stars, the background star on the yellow. If you observe that star, you can see the bright signal. But if between the light travels, while during the light travels, if there is a huge gas or dense cloud, young stellar system, or protoplanetary disk, so if it goes through that cloud and there is actually ice, for example, and that ice usually observe only certain part of wavelengths. Okay? So if the water is there, water observe about 3.2 micron, and the CO2 is there, it observe about 4.28 micron only. So using that signature, you can find, along this line of sight, there's water, ice, or CO2 ice.
If we do find ice, right, does that mean then that star can support life? Like we could find another star that can support life?
So that's a good question. Problem is that SPHEREx is a small telescope. We don't know exactly that is going to the planet or not yet.
Okay.
So, but if you want to really follow the life and the extraterrestrial life, if you actually go to individual these planets, right? So we are not doing that, but we are contributing that where actually ice formed, which environment ice is more, can produce more, and then we can study that, okay, this ice it should usually form this part of the sky, this area, on this kind of physical system. We can learn more about, we have to look at exoplanet around this region, that kind of stuff. So this is how SPHEREx can contribute and what's the technology behind the SPHEREx. And then I think that since people start engaging at the sky at the beginning, now we are studying the universe through these fantastic technologies and instruments, and then there will be much more to be discovered. So we are asking many questions in the humanities, asking when they look at the really dark, beautiful skies, we ask countless questions. But that question is now can be addressed by the science and astronomy and space telescope. So this is just beginning, and there's so much more to be waited to be discovered.
So, Doctor, we've actually learned about so many different fields of science. We've done robots, mathematics,
cool.
AI, quantum computing, and now space.
Yeah.
So, do you think that as time progresses, will all these fields of science sort of synergize together?
Oh, of course. I think that, for example, robot. What can you think of the robot can help astronomy? Can you imagine something?
For like the moon, no, they can go and
Yeah, you can rover.
like,
And also in my case, let's say if my space telescope is broken, right? And you can send the robot and then actually fix it, right? Right now, the space telescope is only orbiting very near Earth. If we really go far away, human cannot travel a million kilometers away. Can send a robot. Robot technology can help, for example. So you can fix it. Telescope, very expensive telescope, like JWST, is orbiting 1.5 million kilometers away from us. Math is actually very important. I mean, math is basis, right? Math is always correct. Yeah, science sometimes wrong, and you can give you a tool analyze the movement and all the analysis. For example, Newton invented calculus, integral, derivative. He invented that to calculate motion of the moon and the planets. Okay, he invented calculus and physics together and astronomy together. So that's all connected. AI is obvious, right? So right now we have 3 million images at the end. Our mission, 3 million images. You cannot analyze all of that, obviously. I want to, but my life is limited. So AI and this machine learning technique can help this kind of the analysis. Probably quantum computing is brand new. Quantum computing means that huge computing powers, right? So in the astronomy and the space mission, sometimes you are limited by, not by money. How fast you can calculate something is sometimes limited. If you can calculate really fast, all the problem is go away, right? So if the quantum computing can drive this really huge computing power, our life is getting much easier. Astronomy is actually very sensitive and very eager to produce advanced technology. That's because the astronomy is very sensitive to this kind of faint emission, right? We are talking about a billion light years away source. We are detecting really dim light, right? So astronomy in nature very difficult. So the demand for the level of technology needed for this kind of space telescope or probe, others are very high. So usually you don't need that kind of quality in the ground, but the space telescope and this kind of astronomy mission is require huge technology. So we drive the basic technology to the edge, and then that technology fall back to the actual real life and the engineering few years or tens of years later. So that's the kind of the astronomy and other field of the science, research, and engineering kind of talk together and synergize. Yes, today we studied how SPHEREx actually explore this universe and how was the technology and the science cases behind it. So this is just beginning, and then there are so much questions to ask. So there are countless questions to be answered in this area. I think that asking these kind of questions is starting point of the whole science and kind. I hope you guys keep supporting us in Space Telescope and astronomy and keep asking questions. Thank you.
Thank you.
Thank you, Doctor.
질문 가겠습니다.
Robot intelligence experiment. So when I came here, I did a really fun project.
We need to find the pattern. How AI turns the kind of issue. Oh, 진짜로?
Need efficient sleep. Big pleasure.